It's a very great pleasure to me to be invited to give one of the London Mathematical Society popular lectures, because I have always tried to dissipate the unfortunate impression that so many bright, intelligent people get that mathematics is a dull, dreary subject, which it certainly isn't. Of course, what is dull and dreary is elementary arithmetic, the kind that all our long-suffering students meet in primary school and for the next few years, which is horribly uninteresting. You might describe it as the cholesterol of the educational system, clogging the arteries of learning. Genuine mathematics, I contend, is exciting. It's also one of the most permanent of the achievements of human beings. And that is one of the points that I want to bring out in my talk to you today, because the ideas I want to talk about originated in the 12th century and are still exercising the attention of mathematicians today near the end of the 20th century. The man who started these ideas is a rather well-known Italian, the name of Fibonacci. He was a merchant of Pisa, and Fibonacci's real name was Leonardo of Pisa. And he lived approximately from 1170 to 1240. Strangely enough, there seems to be doubt as to the year of his birth, doubt as to the year of his death, but very little doubt that he lived for 70 years. Because if you look up certain authorities, the dates, for example, are given as 1175 to 1245 and 1180 to 1250. At any rate, he can be credited, among other things, with one of the greatest achievements, which is bringing the Arabic numeral system to the Western world. But he observed that a certain sequence of numbers, now known as the Fibonacci sequence, occurred in plant growth. And many people have asked themselves why. If you just like to look for a moment at this chart, you see all sorts of examples where the so-called Fibonacci numbers occur in nature. I'm particularly fond of this example of the pineapple, where you count the spirals going round the pineapple, the spirals of the scales. If you go to buy a pineapple, it's no good pressing it to see if it's soft and to decide whether it's ready for eating. What you want to do is to see whether, when you go the long way round, you find there are 21 rows, and the short way round, you find there are 13 rows. Then you know you should buy it. If they're 13 and 8, it's not ripe yet. If it's 34 and 21, then it's overripe. But in all these other examples as well, you find the Fibonacci numbers appearing, particularly with pine cones, with the symmetries of various flowers like the daisy and the buttercup, and so on. And there have been many attempts to explain this. And actually it appears that the explanation is a very simple one, which is simply a matter of nature conserving energy. In fact, I have here a quotation from a very recent article. You see, the hypotheses about these Fibonacci numbers were made in the 13th century. This explanation appeared in 1992. So you can see how constant has been, indeed, the interest in these Fibonacci numbers and their relation to nature. These two French physicists, Douady and Coudet, writing in Physical Review letters, as I say, in March of 1992, concluded that the Fibonacci pattern emerges as the system keeps the energy required to a minimum. In other words, the spiral growth in plants needs no special botanical explanation. The new elements in the pattern, be they florets or oil drops, simply appear where they need least energy to do so. Amusingly enough, the Fibonacci numbers also appear in the laws on the growth of the size of a rabbit population. And there again, perhaps it's not too fanciful to say that the explanation of the expenditure of least energy is probably the correct one. But I'm not going to talk to you today about the scientific applications of Fibonacci numbers. My intention rather is to talk about the mathematics of these Fibonacci numbers. And I want to start by showing you how you can do a rather remarkable number trick. So I want you to see carefully how this number trick would be done. You write down for the people at your party or people in your audience what you see here on this slide, just 0 down to 9. Then you ask a volunteer to enter in the rows 0 and 1 any two numbers. But so that the trick doesn't take too long to achieve, suggest to them they just enter two small positive integers. And you yourself are not supposed to see what those integers are. So let's just say, for example, that your volunteer, well, you of course are away in another room, writes down 3 and 2. So then you ask all the people in the audience to do exactly what your volunteer has done, and then to begin the following process. To enter in row 2 the sum of these numbers 3 and 2. That would be 5. Of course, this is all done silently. You don't hear what these numbers are, but the audience are doing it. Then to enter against 3 the sum of 2 and 5, 7. To enter against 4 the sum of 5 and 7, 12. And so on. 19, 31, 50, 81, 1, 3, 1, against 9. Of course, you are back in the room, but you don't know what numbers were entered against 0 and 1, so you don't know any of those numbers that I have been writing down that you'll see there on your screen. Now you say, well, these tricks sometimes fall very flat if there has been some sort of arithmetical error. So just to make sure that everybody has got exactly the same, let me just check, say, what people have written down against 6. So somebody admits they have written down 31. Somebody else says, yes, I also wrote down 31. You ask people, did you all write 31? They say yes. So you say, well then, I suppose you've all got the same. Now you ask them to do something else, and this explains particularly why you ask them to choose small positive integers to start. You say, add all those numbers up. So laboriously they do it. Perhaps they use their hand calculator. 5, 10, 17, 29, 48, 79, 129, 210, 341 they get. And then you reveal, and I leave it to you to decide how you reveal it, that you had already known that the sum would be 341. And I can assure you that they're very impressed. How on earth did you know that the sum would be 341? Well, I'll tell you how you knew. Because, of course, all this talk about wanting to check that everybody had the same sequence of numbers, so you checked what the entry against 6 was, and they all agreed it was 31. That was all very dishonest of you. You wanted that number 31. And why did you want that number 31? Because all you had to do was multiply it by 11, and that would be the sum of all the numbers. So what you did, while they were laboriously adding these numbers, and believe me, if they'd chosen bigger numbers than 3 and 2, it could have been very laborious, all the arithmetic they did. All you did was to take this 31 that they announced here and multiply it by 11. So there is the trick. Now I want to show you why the trick works. So here we have the general case. The volunteer has chosen the numbers A and B. A you see against 0, B against 1. And now we follow the instructions. That is to say, against 2, we write the sum of what we wrote against 0 and 1, A plus B. Against 3, we write the sum of what we wrote against 1 and 2, A plus 2B. And so on, all the way down to 9. I've highlighted 6 for you again here. Notice what we see here, 5A plus 8B. Over here, I've written what we call the running totals. That is to say, the sum of all the numbers so far written down over here. So against 0, just A. Against 1, we've written A and B, so the running total is A plus B. Against 2, we've written A, B, and A plus B, so the running total is 2A plus 2B, and so on, going all the way down. And here's the crucial one. Against 9, you see we have written 55A plus 88B. 55A plus 88B. Obvious factor of 11. Dividing out by 11, you have 5A plus 8B, which is what we have against 6. So whatever A and B are, the trick will work. Well, that you can say is the explanation. And to some that may be totally satisfying, but it would not be to a mathematician. And actually, in my experience, it isn't to inquiring students. Because they say, does that only happen in this place? Does it only happen when we have the 6th entry here and the 9th running total? Surely it must happen in other places, and indeed it does. If I draw your attention to what we see against 5, on level 5, here we see 8A plus 12B. Clear factor of 4, producing 2A plus 3B. There is 2A plus 3B. So it's happened there too. But there are other questions. Why do you get the factor 11? Why do you get the factor 4? And it's these things that I would like to try to explain to you. What you might call the real explanation behind the trick. Why do these particular numbers play this special role? I might just make a remark here about the nature of explanation in mathematics. There's an awfully silly notion around that many of you may have met in your own school days, or may still be meeting if you're still school students. And that is that one can learn for mastery, and that the teacher can teach for mastery. This is rubbish. In mathematics, there can never be mastery. Whenever you have an explanation, it must raise further questions. This explanation here of the number trick I showed you only raises further questions. And you can only have the impression of mastery, in my judgment, if you know a great deal about what's gone into the problem, but you know absolutely nothing of what happens after the problem. There must be total ignorance beyond the problem to create this delusion of mastery. So don't pay any attention to all this talk about mastery. In mathematics, it's unattainable. Mathematics goes typically from answer to question. There are always more questions. So I want to discuss with you these questions. But before I put this slide here, this overhead slide, to one side, I just want to draw your attention to what we call the coefficients. What are the coefficients of A if I go down this column? 0, 1, 1, 2, 3, 5, 8, 13, 21. These are precisely the Fibonacci numbers. Here again, 1, 1, here they come again, 2, 3, 5, 8, 13, 21, 34, and so on. There's a remarkable thing. Something else one notices about these tables here. If you look down here, you see that the numbers here are extraordinarily like the numbers here, but staggered by 2 places. We just start here, for example. I see here 3a plus 4b. Here 3a plus 5b. Here I see 5a plus 7b. Here 5a plus 8b. Systematically, the numbers I get here have as their coefficients, the case of A, exactly the same as the coefficient of A 2 places down. In the case of B, 1 less than the coefficient of B 2 places down. So we have all sorts of now of interesting evidence for what we call conjectures. We have conducted what in mathematics we would call an experiment. Don't let people tell you that you can't do experiments in mathematics. You can only do them in the experimental sciences. We constantly experiment in mathematics. We look at these particular cases, and from the particular cases we try to generate true formulae. And as I say, the number trick itself, we are convinced, must be an example, a special case of a general formula, saying that the number here is 11 times the number there. And here, explicitly, I want to bring in the Fibonacci and the Lucas numbers. Concentrate your attention first on the part to the left here. So for various values of n, I've listed the Fibonacci numbers in the first column. I start here, as you notice, at n equals 0. If any of you have read about these things, you'll often find it started at n equals 1. From the mathematical point of view, it makes much more sense to start at n equals 0. And here are these numbers which have come up. They came up over here. They came up in the number trick as coefficients. Here they are, 0, 1, 1, 2, 3, 5, 8, 13, and so on. Those are the Fibonacci numbers. Now what about this remarkable man, which I've been calling him Lucas. I should really call him Luca. So let me just say a little bit about him. Luca is a Frenchman, as you gather, that's why I say we should say Luca. Edouard Luca, 1842 to 1891. As you see, he died rather young. It was a very tragic story, and a story which I found very hard to believe. It appears that he was at a banquet in Paris. Somebody inadvertently dropped something on a jug. The jug shattered, and a shard from the shattered jug jumped up, hit him in the cheek, made a very serious wound in his cheek, and he developed erysipelas, and he died of poisoning. It's, I say, a most extraordinary and tragic accident. And he was a marvelous man, I mean, full of the spirit of inquiry about numbers. He was fascinated by numbers and made many, many very significant advances. He was fascinated by the Fibonacci numbers. And he had one extraordinary idea. I say extraordinary because I don't quite know exactly what his insight was. But he said, obviously, this way of generating sequences by at each stage adding up the two previous numbers is of great importance in science as well as mathematics. See, in our number trick, we generated our sequence that way, and of course the Fibonacci numbers are a special example of that. We go back here. See, of course, the Fibonacci numbers 0, 1, 1, 2, 3, 5 are, of course, generated in exactly that way, starting with 0 and 1. So Luca said, let's try starting with 2 and 1 instead of 0 and 1, but using the same rule for generating the sequence. Obviously, he's not going to start with 1 and 1, because that just produces the Fibonacci sequence, but off by 1 index. So he said, let's start with 2 and 1. Some people believe that he was inspired to do this because he saw a connection with some of his own work on detecting prime numbers. I would be very, very interested to know if that's true. At any rate, he produced this sequence here. 2, 1, then 3, you see, 2 plus 1, the 4 is 1 plus 3, and so on. So I produced them for you for quite some way there, but it's not so important that you should try to memorize these numbers, just how they are generated. So now I just want to show you what was on the right-hand side of this slide. This is more mathematical language. You see, what I say is that both the Fibonacci numbers Fn and the Luca numbers Ln satisfy the same, what we call, recurrence relation, that the n plus second term is the sum of the n plus first term and the nth term, but with different initial conditions. The initial conditions for the Fibonacci numbers were that they started against 0, we wrote 0, against 1, we wrote 1. With the Luca numbers, against 0, we wrote 2, and against 1, we wrote 1. And here I've just written down some of the relations which students have themselves observed by just looking at the tables I showed you. They observe, for example, that the Luca number Ln is the sum of the n plus first Fibonacci and the n minus first Fibonacci. We go over to the left-hand side again, just so that you can just see what they observed. They observed, for example, that this 7 is 2 plus 5, that the 11 is 3 plus 8, and so on. We call those linear relations, those two, because they only involve those numbers to what we call the first power. They're not multiplied by each other, they're just added, and they only appear to the first power. Here's what we call a quadratic relation that was observed by students. That's quadratic because, you see, the f is multiplied by the l. Let me put it at the center here, or to the center. F, 2n is fn ln. They observe that that's a quadratic relation. Now, I cannot go into all the detail of the mathematical reasoning, but let me challenge you to see if you can see why what I'm about to say is true. I say when you have a linear relation, it's terribly easy to prove it, because all you have to do is to see whether it's true for 2 successive values of n. And if it's true for 2 successive values of n, it's always true. That's because You have a linear relation, and the recurrence relation generating those sequences is a linear recurrence relation. So linearity is a terribly important idea in mathematics, and I do wish that it was stressed much more than it is at all levels where it would be appropriate to do so, because we can do things with linear relations which we cannot do with nonlinear relations. And indeed, the modern mathematical theory that many of you will have heard of is called chaos, which arises precisely when you lose linearity. Lose linearity, and what do you have? Chaos. If you have linearity, you have control. This is another relationship at the bottom to which I draw your attention, a very crucial relation which many of the students that I've had have noticed, that the fn's are even precisely when the ln's are even, and that happens exactly when n is divisible by 3. That's what that mathematical symbol there means, when n is divisible by 3. To prove that, all you have to do is write down the remainders when you divide by 2. That's, say, the 0 stands for evens and the 1 stands for odds. So you get even, odd, odd, even, odd. At that point, you're finished, because since 0, 1 has reappeared, the whole pattern must reproduce itself from then onwards. And so you get 0, 1, 1, 0, 1, 1, 0, 1, 1, exactly this rule. So now I want to go back to the number trick and to try to understand it. Because what you may have noticed is this. When I gave the two examples of the number trick, the multipliers were 11 and 4. And you notice that those are both of them Luca numbers. So we formulate what we call a conjecture. What is a conjecture? That is something which we hope is true. And what is our conjecture going to be? Well, our conjecture is going to be based on this observation. The observation was that if we sum, and I use the mathematical notation, from 0 to 9, all those numbers un, what we saw that we got was L5 times U6. We had one other example, I won't write it down, but that's precisely what we observed. Summing everything from 0 to 9, we got a multiple of the term against the level 6, if you remember, U6, and the multiple has turned out to be L5. So this is now our conjecture, the result which we believe will always be true, and I want to see if we can see how we might prove this. It is what we would call a generalization of that statement there. It says that the sum from n equals 0 to 4k plus 1 of un is L 2k plus 1 u 2k plus 2. Now I would claim, if that is true and if we can prove it, we have explained the explanation. That is to say, what we had here, which we did verify was true, is the explanation of the number trick. But that explanation generates the obvious question, why is that relationship true? And we say, because we always have this relationship. Of course, as I emphasized earlier, that's not the end of the story. Inevitably, we ask, why should we have this relationship? Are there other relationships like it? The answer is yes, there certainly are. And if I had 3 hours instead of 50 minutes or so, I could go into that. But let's be content, let's not be over-ambitious. Let's see how would we go about proving this. Well, now I claim that we observed from an earlier slide 2 facts. One fact that we observed was that if we added up all the entries of those UNs up to the nth, what we got was the entry 2 places lower down, but we were short by 1b. So that was an observation we actually made earlier. How would we go about trying to prove that? Now that sort of thing is very easy to prove. There's a standard way of proving results of that kind. It's called proof by induction. We regard this statement as a statement about the number capital N. We want to prove that it's true for all values of capital N. So what we do is we say, is it true when n is 0? Well, in the case of n equals 0, on the left there, all we have is u0, but u0 was a. On the right, we have u2. If you look back, you'll see that u2 was a plus b. So for n equals 0, our assertion says that a is a plus b minus b. Obviously true. Then we have to do what we call the inductive step. The inductive step says, suppose it's true for n. So if it's okay for n, then we say, is it okay for n plus 1? Well, what is the summation of the un going up to n plus 1? Well, that's the summation going up to n plus un plus 1. So that would be, I write the un plus 1 first, plus the summation going up to n was un plus 2 minus b. But un plus 1 plus un plus 2 is un plus 3. That's how these u's were generated. So there we have it. So yes, okay. So if it's okay for n, it's okay for n plus 1. That is the inductive step, so the whole thing is okay. That is proved. So that is proved. But there was another observation that we made, which I want to recall. We made the observation that in fact the un was a certain multiple of a plus a certain multiple of b, and those multiples were Fibonacci numbers. So precisely what we observed is that the nth u is Fibonacci n minus 1 times a plus Fibonacci n times b. How would we prove that? There we have linearity. That is a linear relation as far as the Fibonacci numbers are concerned. If it's true for 2 successive values of n, it's always true. I leave it to you to complete the demonstration. That's trivial. It's okay. So we can now analyze what we're trying to prove. Let me write it down again, what we're trying to prove. This was our conjecture, a complicated conjecture. It's that if we add up all those numbers, what we get, the claim is L2k plus 1, U2k plus 2. Sorry, I've left out the UN there. Very bad. There's the UN. But now, the first improvement we made was to say that this thing on the left here is simply U 4k plus 3 minus B. So the equivalent conjecture is what I am now writing down. Now I invoke this relationship here to change that. So now this conjectured equality becomes F 4k plus 2 times A plus F 4k plus 3 times B minus B is equal to L2k plus 1 times. Now I'm going to just do that so that you can concentrate on this. What is this? U2k plus 2. That is F2k plus 1 times A plus F2k plus 2 times B. First sight, it may appear to you as a long line, it's a lot of writing there. Things have got worse, not better. Why can I say they've got better? Because if we claim that this is true for whatever numbers A and B we take, then it must be that on the two sides of this equality, the coefficient of A is the same and the coefficient of B is the same. So therefore, this awful long line is equivalent to two statements. If I look at the coefficient of A, I have F4k plus 2 on this side, and on the other side I have L2k plus 1, F2k plus 1. And if I look at the B, I have F4k plus 3 minus 1, and on this side I have L2k plus 1, F2k plus 2. So very interesting that we have now written down two identities conjectured about the Fibonacci and Luca numbers, which will totally explain and prove this identity that we got interested in here. See, now we have no more variables in the story. These are perfectly definite numbers. We want to prove these things true. And we have bridged some 600 years here. These Fibonacci numbers, as I say, were invented at the end of the 12th century, and the Luca numbers were invented at the end of the 19th century. And another 100 years on, we find ourselves wanting to prove these two relations between them. And actually these relations, again, were relations which students observed by looking at the tables, with a little prompting, let me be absolutely honest, in the case of the second one, but they did observe them, and they observed others too of the same kind. So here we are at a sort of halfway stage in our argument. We have now reduced it to proving things about the Fibonacci and Luca numbers. So we started off with no mention of Fibonacci and Luca numbers, and we find ourselves talking about the Fibonacci and Luca numbers. Can we prove those? Well, I'm going to leave that available to me because I would like to have it available at the end when I can announce in triumph, see, we've proved it. But we don't have a technique at the moment for proving things about the Fibonacci and Luca numbers. But actually, work of that kind was done in the 17th and 18th centuries, because we are dealing here with a linear recurrence relation. Now, I could be more general here, but I don't propose to be. I want, as I say, suppose then, this is quite sufficiently general, I'm dealing with the recurrence relation un plus 2 is un plus 1 plus un, with initial values u0 equals a, u1 equals b. I want a formula for un, and I'm going to apply the formula afterwards to the Fibonacci and Luca numbers. In the case of the Fibonacci numbers, a would be 0 and b would be 1. In the case of, let me write that down, in fact, f0 equals 0, f1 equals 1. In the case of the Luca numbers, L0 is 2, L1 is 1. See, the same recurrence relation, different initial values. How do we, as we say, solve such recurrence relations? Well, first of all, I make a statement which is so obvious you might not think it's necessary to make it, but it's terribly important. I say, obviously, the numbers un are determined by the recurrence relation and the initial values. It's perfectly clear. There can be no doubt. If you know the two initial values and you know the recurrence relation, in principle you know all the values of un. They're fixed. So, the consequence of that obvious statement, and don't think obvious statements aren't worth making because they often are, but the consequence is that if I can find expressions, functions of n, which satisfy that recurrence relation and satisfy these initial values, that's un, because the un is determined. So I first make this observation. I say that the function x to the n, or if you like, un equals x to the n, satisfies the relation let me write star here to avoid having to keep on rewriting it. The relation star if x squared minus x minus 1 equals 0. Because, of course, x to the n satisfies that if x to the n plus 2 is x to the n plus 1 plus x to the n. But, of course, divided by x to the n, if that is true, then if you like multiplying by x to the n plus 2 will be x to the n plus 1 plus x to the n. So I want some names for the solutions of that equation. I just want names for them. I don't want to solve the equation. Unfortunately, students are very uncomfortable leaving equations, as it were, unsolved. But let's just say that these equations here, so let us write alpha and beta. They're nice letters. Let alpha and beta be the solutions of this equation. The solutions of, and I'll call that double star. Double star. I say I don't want to write down what alpha and beta are, but it might well be important, and it often is, to observe that, of course, alpha plus beta is then 1, and alpha beta is then minus 1. Because when you have a quadratic equation, the negative of the coefficient of x is the sum of the roots, and the constant term is the product. Now I make again an observation that all has to do with linearity, the key to every method you use in this connection. If, I say now, if un equals vn and un equals wn satisfy star, so does un equals rvn plus swn for any constants R and S. That's, again, as a just linearity. I strongly recommend you to verify that for yourself. Remember, mathematics is not a spectator sport. If you're really to appreciate mathematical arguments, you must carry them out yourselves and see that they're right. You cannot, of course, learn to do mathematics without doing mathematics. What is the strength of that observation? The strength of that observation is that since we've got two solutions of star, namely un equals alpha to the n and un equals beta to the n, these are solutions. Are solutions of star. So, here's the punchline. Un equals r alpha to the n plus s beta to the n is a solution of star. Now we've really come a lovely long way. We know the general solution, in fact, of that recurrence relation. Now what are we trying to do? Remember, we're trying to find that solution for which u0 is A and u1 is B. So we just determine R and S to give us those results. So I put n equal to 0, I get A is equal to R plus S. I put n equal to 1, and I get B is equal to R alpha plus S beta. So those two equations enable me to determine R and S. Excuse me. Lovely. Let me draw your attention here, since I made a break anyway, to this justification for starting at n equals 0. You get much easier equations. If you start with n equals 1, you'll have something telling you about R alpha plus S beta, and something telling you about R alpha squared plus S beta squared. Much more complicated, and quite unnecessarily so. So here's a payoff for starting at 0. Right. Well, again, I don't determine R and S from those equations. I'm not compelled to solve equations. But I'll look at the special case. Let's look at the Fibonacci numbers. What happens in the case of the Fibonacci numbers? The alpha and beta are exactly as they are here, the solutions of that equation, x squared minus x minus 1 equals 0. And what do we have here? Fibonacci 0 is 0. So 0 is R plus S. Fibonacci 1 is 1. R is 1 is R alpha plus S beta. Solving for R and S, and this time now I will solve, we find that R is 1 over alpha minus beta, and S is minus 1 over alpha minus beta. So substituting to the top, we find that Fn is equal to alpha to the n minus beta to the n over alpha minus beta. Now, see, there's a beautiful formula for Fn. Now, some people might say, how can you say that's a beautiful formula? Certainly, it's not a useful formula if I were to ask you what is F11. To start substituting n equals 11 into that, and then saying alpha and beta are roots of x squared minus x minus 1 equals 0, that's not going to be helpful. But it's a beautiful algebraic formula. Algebraically, it's enlightening. Arithmetically, it isn't. And that's a real distinction. Let me talk about the Luca numbers. What happens here? In the case of the Luca numbers, you remember they start 2, 1. So it's the same alpha and beta, but now 2 is r plus s. And 1 is r alpha plus s beta. Now you might go ahead to solve those for r and s. But you might look back at what we were doing earlier. Let me just point it out to you here. In our earlier work, we saw that alpha plus beta equals 1. Alpha plus beta equals 1. So if you look at this, remembering that alpha plus beta equals 1, you might immediately spot that the solution is the very simple one, r equals 1, s equals 1. So, Luca number is this formula with r and s 1. So it's an even, in some sense, more beautiful formula, just alpha to the n plus beta to the n. Now we have really made enormous headway. We have these lovely algebraic formulae for alpha and beta. And these are going to do the trick for us. Because I claim, first of all, I'm going to rewrite them and then I'm going to make certain claims immediately. Here is what we've got. Remember, Fn is alpha to the n minus beta to the n over alpha minus beta, and Ln is alpha to the n plus beta to the n. Well, I claim that from there, the fact that F2n equals Fn Ln is absolutely obvious. It's just difference of two squares. And you should notice that one of the identities that we wanted to prove, this first one here, of course, is now proved. Because, of course, F2n equals Fn Ln has as a special case that F4k plus 2 is F2k plus 1, L2k plus 1. So this is already okay. So we're very, very close now. We just got the second one. But I propose, if you like, my final fling with you is to point out that it usually pays off to prove a little more than you want if it's just as easy. So I want to take a look at what happens when I multiply Fm by Ln using those formulae. Well, what I get is alpha to the m minus beta to the m over alpha minus beta times, I'll put it like this, times alpha to the n plus beta to the n. So we do a little bit of algebra. We get alpha to the m plus n minus beta to the m plus n over alpha minus beta. And what about the other terms? Well, we get plus alpha to the m beta to the n minus alpha to the n beta to the m over alpha minus beta. Well, what's the first thing here? Well, the first thing here is just Fibonacci m plus n from our formula. What about the second one? Second one, a little more complicated. I take out the factor alpha to the m beta to the m, which I just write as alpha beta to the m. What do I have? I have alpha to the m minus n minus beta to the m minus n over alpha minus beta. So what's that? Well, I can't do any better than fm plus n here. What about this? What is alpha beta? Again, I remind you from that quadratic equation, alpha beta is minus 1. So that's minus 1 to the mth. And what is that? Fibonacci m minus n. So we have this beautiful formula that if I multiply Fibonacci m and Luca n, I have Fibonacci m plus n plus minus 1 to the mth Fibonacci m minus n. That formula is in fact the only important nonlinear relation connecting Fibonacci and Luca numbers. What is its relevance here? Well, let me put back here this formula that we're wanting to prove. See it down here?
If I could just stop you there.
Yes.
Right. Okay, we're ready to go now.
So this is all that we're left wanting to prove, and this is proved by the great formula that I just wrote down and removed from the screen. You just have to make the substitution and remember that f of 1 is 1, and that formula drops out. So we've proved those two formulae, so let me remind you what that means. That means that we have explained the explanation of the trick. But we've done much more. We've begun a serious mathematical analysis of these two crucial sequences of numbers. That is typical of mathematical development. And I hope that you will go forward yourselves to study more about these amazing sequences of numbers. Thank you very much.